No, that's not on the stack, right? Well, let's check that later. The constant argument against C++ is that it's slow. And C++ can certainly be a horribly slow language. But it can also be a fast language. So there are some things that can be seemingly horrible in C++, the standard template library and template metaprogramming. So those are essentially programs that are executed during the compile phase. You can use that not just to generate containers or so, but you can actually do flow control with this. So normally if I had a theoretical function here that in plain C here, I have two arguments there, choice A and choice B. Depending on those choices, I would have different paths and say maybe some different loops here. Well, I don't know what those choices are at compile time here, so that I can't really, all these conditionals will have to be, I will have to go through them dynamically when I execute the code. But maybe I know in practice they can't be any integers. Maybe there are only 2 or 3 values these integers can take. So in C++, you can let these be template parameters. And then these template parameters, if the compiler knows what all the possible values are at compile time, I will expand this to different objects in the object file. So if there are 4 different combinations of them, it's actually going to be 4 different functions. But in each of those functions, all these conditionals will have been removed. And if this is now complicated logic, such a code might be 10 times faster than the code that has to dispatch this as runtime. Now, the price for this is that you can have slightly complicated and ugly function definitions and everything, but for a program like ours, where speed is everything, we have a whole lot of cases where C++ is significantly faster, not just than C, but even significantly faster than Fortran. But of course, it requires some care. So how do you know this? How do you know if the compiler does its job here or not? Well, there is a beautiful site called godbolt.org. So if you have a small code, say int square, I just square a number. And if you go to Godbolt, there are drop-down lists, and then you can see, for this small program, what will the assembly code look like on x86-64 compiled with Clang, or ARM64 compiled with MSVC, or maybe ARM64 compiled with GCC 9.3. Do you see here that the MSVC compiler and the GCC compiler, they generate slightly different assembly instructions? And in this case, it probably doesn't matter. But if you have a sensitive code base here and suddenly it's 10% slower, you can use Godbolt to check exactly what is the difference in the assembly language code generated by your small code. It's very advanced, but it's a really cool way to go. If you care about literal cycles in your performance, this is kind of my favorite site on the internet. We talked a little bit about modularization. Modularization to me is really not, neatness is certainly nice, but the reason I want this neatness is primarily to prevent bugs, because I hate spending time in the debugger. Even if you have many different files or modules or so, what happens after a while, if you don't deliberately spend time cleaning up your code, Erwin includes my header, I include Erwin's header, and then Erwin includes somebody else's header. And what suddenly happens after 10 years, if you draw a dependency graph of this, it's going to look something like this. This is an actual dependency graph from an actually fairly small project. So pretty much everything depends on everything. The great thing, if there is a bug here, we know that it is somewhere. Yes, it is somewhere in my project, up 2.5 million lines of code or something. Completely impossible. Now, if you instead make sure that you never, ever have circular dependencies, neither between your classes nor between your files, and in principle there should be one class per file, so that the top level file here, this is from GrowMax, the top level file includes one layer of objects here. Those in turn, classes, those in turn include more. I'm only showing that for the top level class. That in turn includes others. They can never, ever go back. And we have the same setup for header files. Never, ever circular dependence in header files. The neat thing here that if there is an error here, it's going to be much easier to trace it. And I'm going to show you ways that we can do this automatically later on. So for instance, if I know that something is wrong in the GMF abstract analysis array data, it's either in that class or the windows underneath it. The error can't be in the things that I don't include. Where that gets really powerful is when we combine it with unit testing. So you probably all test your code, and you test it by running through it and make sure that you got the same results that you got last week, right? That's great, because you're now ensuring that you have the same bugs you had last week. Regression testing is that. That's completely different from unit testing. We love to do unit testing. There are a number of frameworks. I happen to love the one that's called Google Test. It's a fairly simple test framework, and that in my class, API, whatever you call it, those promises you've just made, that if you construct it this way, you're going to get 10 random numbers back. This is where you check on those promises. So that Erik promised that you would get these 10 random numbers for this seed. Check that we actually get those 10 random numbers. And that might seem like a completely stupid test. But those simple, stupid tests frequently detect things that are completely impossible to find bugs otherwise. So for instance, check rounding. That's how stupid. 4.6, that's going to round to 5, right? Or 4.5, well, either it will round to 4 or 5, but that's not going to change. Well, thank God we had tests for this. And this has to do with some CPUs both have a SIMD unit and a normal unit. And roughly 10 years ago, we realized this test found a bug because IBM, in their great geniuses, they decided to use different rounding modes for the SIMD registers versus their normal floating point registers. And your algorithms, many numerical algorithms, depend on these rounding modes. This would have been a bug that would have stuck with us for 10 years. And once in a blue moon, when you have to have exactly the value 4.5 and then just zeros exactly. This is one of those things that happen once every 10 billion calls to the routine, right? We found it the first time we tried their new compiler. And that means that the bug never hit me. So instead of spending years on the debugger, the unit test and the encapsulation saved me. I never even had to open it. When we saw this, we knew when this unit test fails, I already know there's probably 5 lines of code that the bug must be located in. Fixing it in 5 lines of code was just a matter of testing what the output of the instruction was when it failed, and boom, then we found the error and reported it to IBM. And there are numerous compiler bugs we find this way. So don't assume that a bug is due to your code being faulty. It's actually quite common that the vendor or the compiler author here has screwed up instead. So ideally in C++ or any other languages, you should have exhaustive tests. You should test everything. And I know it might not be realistic for large old programs, but if you're writing those 10 lines of code, try to test every single method, every single procedure function that you create, and test them virtually exhaustively. Because if you have exhaustive tests, like I had for my random number class, then I know I've tested all my promises. All the promises I test, I know that I'm fulfilling them. And then it's no matter of thinking about whether there might be a bug or not. I know if the tests pass here, there cannot be a bug in this code. And knowing that for certain saves so much time. And I'm going to show you why later on. The cool thing is when we combine this with automation so that you don't even have to run these tests manually. We've included the Google tests in this small repository too, if you want to use them. They're not very hard to write. So let's now assume that you've grown here, or you have a large old project like ours where you retrofitted it with tests. So you now have 1,000 classes. But thank God you don't have any circular dependencies. And then now there's a bug. Sorry, I did something wrong. Sorry for committing this to your project. Normally, you know that there is a bug somewhere in 1 million lines of code. But in this particular case, we had unit tests for all of them. So when you run this through, this is the result. So all the green unit tests pass, the red unit tests fail. Where is the bug? There could, in theory, be multiple bugs here, right? But we know that the top left red one, we definitely have one bug there. That is a promise we're not fulfilling anymore. Start by fixing that one, and then rerun the unit tests. In all likelihood, there was only one bug, and then you're going to see everything being green. But the point here is that if this test corresponds to one function that has, let's say that I was a little bit bad and I had 50 lines of code in this function, I've isolated the bug to 50 lines of source code before I've even opened the editor. I hardly open the debugger anymore because our unit tests have already done the job for me. The unit tests have isolated where my bug must be. So just checking what the values here are and why it fails, normally I don't have to open the debugger. And in particular, all the green ones are completely pointless to look at because we know that my promises are fulfilled there. If this was not 50 lines of code, but 10 or 5 lines of code per function, it's even better. So this is the reason why you want your functions to be so small and why you want to test everything exhaustively. Again, this takes a few hours when you're writing it for a method, but the time you save is that you're not going to be spending any time debugging or trying to fix things later. Yes? We've certainly had bugs in our unit tests, but you tend, like, if there is a bug in the unit test, that will typically result in the unit test failing. What can, of course, happen is that there is a unit test and there is something that I didn't think of to test, right? And that way the unit test will execute, it's going to say the green light, and eventually there is a user reporting a bug. So what we require in that case, if I ever fix a bug in the code, I also have to add a unit test to ensure that this bug can never, ever reappear. So that certainly happens to us too. No, life isn't perfect, and of course, it's hard to come up with ways to test everything exhaustively. Now, at some point, we also need to put the code here, right? And that's, I'm going to come back to the unit test here in a second. If you already have a Git repository on your laptop, that's the first step. You might have a Git repository in GitLab or GitHub. That's the second step. That's great. Don't do what so many people do, and that, in particular, allow any code to go in directly. Well, maybe if it's in your private repository, you can do that. The problem is that if you run a large project, you can guarantee that there are some users who are not as good as the other ones and that keep committing bad code, like me. And that happens. All of us, the smartest people in my team, they make mistakes. We all make mistakes. So what we've done is I can't commit code. I cannot push code directly to my repository. Nobody can do that. So when I push code, it goes to formal code review. And that means that there is now a so-called merge request from Erik. And that means that my colleagues, they say, Erik wanted to do this modification here and change something. And then my colleagues here comment on something here that, it would be a good idea to change this or that. In many cases, we agree that there's frequently, they can even propose a change, and then there is a button that I will just apply their change directly. Or I might have to actually sit down and modify this commit based on their suggestions. And at some point, they all agree, and then they click approve. And then it's up to me to decide, as a project manager, how many approvals should I need. And in GROMACS, we usually say that we need 2 approvals, but at least one of these approvals have to be from one of the project managers, so that we know two beginner users should not be able to commit code on their own. This takes time, of course, but we find bugs here. We find maybe not code bugs, but logical bugs, things that are bad. Are you aware that you're copying 10 megabytes every time you call this function? And then, oh, you're right, I hadn't thought of that. And it's really irritating the first time, and you have no idea how many times this has saved my ass. And eventually, this thread is resolved. At the end here, everyone is happy. And then anybody, including me, can just click that when this has 2 approvals, it will automatically be merged. But what if there was an error that these ladies and gentlemen here did not find? Well, we can have automated reviewers too. So how do we maintain this quality and avoid breaking stuff when we are too busy to do it ourselves? This is related to this concept of continuous integration, which is particularly important for all these online, the Web 3.0 companies, right, that they're designing web services, but it's equally useful for HPC applications. So when I upload my merge requests, those unit tests that I just designed, they're great, right? But I can execute those, so why should I execute them? I can have a computer execute them. So when my merge request is pushed up to GitLab, GitLab automatically runs this. In our case, I run it on x86, I run it on ARM, I run it on RISC-V, I run it on NVIDIA, I run it on AMD, I run it on SQL hardware, I run it on one GPU, I run it on two GPUs, we run it with debug flags, we run it with optimized flags, we run it with different versions of the Clang compiler, we run it with different versions of the GCC compiler, everything. And you have no idea how many small obscure bugs this finds. Which, and then it's really, now the Microsoft compiler has a bug again. But in many cases, that's a bug waiting to happen, right? It's just that the Microsoft compiler warns about something that the GNU compilers didn't. And sure, it's irritating that I have to fix that, but it's better to fix it now, before it becomes a bug. You can certainly run nightly pipelines or so too. The cool thing with this is that then you see all this, we have that configuration, build, test, post-test systems, we build the documentation here and everything. So that by the time this goes up, I know that the unit tests pass not just on x86, I know that they pass on Microsoft Windows and on Macs and on 10 different compilers. Even if I don't have a CUDA GPU on my laptop, I know that I did not introduce any bug that caused the CUDA build to fail, because in our build system, we have CUDA builds. But that's just the hardware part. Maybe we can be even smarter. There are a bunch of logical tests and things that we test here, integration tests, regression tests. We're checking that we don't have memory errors. And I added 2 slides that you actually don't have in your handouts here that I'm going to show you. Assuming that I have a small, this is a small function here where Erik here has done some stupid things. I did not add curly braces. You know, that's not the end of the world, but it's a bug waiting to happen, right? If I add a second line here, I might get errors in the future. And I've also been a bit sloppy with my indentation. So I can run Clang tidy here, which is basically a tool checking what bugs I have. I get 13 warnings about this one. These are not, the code here is correct, but it's things that are a bit bad practice for modern C++, and things that are bugs waiting to happen in the future. You know, I should use a trailing return type. Using a parameter I is short. You should have at least 3 digits. Make sure that this is more explaining. I have a redundant Boolean literal. Don't use else after a return. It's not wrong, but it's bad practice. And you can, of course, you can choose what things you enable in your project. Here I told it to include the kitchen sink of checks. But instead of doing that automatically, just add the dash fix. So I tell it, why should I have to rewrite this? C-Lang tidy can rewrite my code for me. No point. This is not AI. This is properly hard rules so that you don't have to worry about mistakes here. So this will format the code and do this with properly modern C++ standards, again, according to the configuration files I had here. And now it's good practice. So we do this automatically. We will not allow code to go in if it contains bad practice. But again, it sounds horrible if you have to fix it manually. But just adding the dash fix flag, let the computer do the hard work and save you from it. We might have errors too. Can you spot any error in this code? It's a bit small, perhaps. Can anybody see any potential error here? Sorry? Yes? Divide by 0, yes, on line 7. That's bad. Congratulations, you're just as smart as the compiler. The compiler finds this too. It's just a warning, but it's certainly bad. But there were 2 more bugs here that we didn't find, and the compiler didn't find them either, because they're logically more complicated. C-Lang has a static analyzer. So if I do the C-Lang static analyzer with just -- analyze commands, the modern version of Clang, it will find 2 more things. There are another division by 0 and a potential undefined or garbage value returned here. That's hard. Why can that happen? Then I need to understand the logic here. C-Lang to the rescue again. I can tell it to generate the output in HTML here instead. And then I get small HTML pages here that, in the first case, certainly divide by 0 on line 7. Another case, if b has the value 4, on line 8, I can compute c as b minus 4. Now c will be 0, and on line 8, I then divide by c. That's another potential divide by 0 that we missed. Second, if b has any value Different from 1 or 4, I'm going to return A, but I never set A. So then I'm returning a garbage value. You can even do this between different translation units. So we run through the static analyzer automatically for every single commit we do. You have no idea how many obscure bugs this finds. And again, I might know that this can only have the value 1 or 4 until a colleague uses this module in some other way, and the value can suddenly be 3, 2. And then that bug happens, right? The other thing that are equally powerful tools for memory sanitizers and thread sanitizers, finding these obscure things that if you happen to be writing to memory, or if I happen to access an array out of bounds or so, Clang can analyze that for you at compile time. It takes 2 seconds, and then it's going to save you a month of time in the debugger. So it's probably worth for you to spend a few minutes setting these things up in your modern repository, and this is in particular why I love modern versions of Clang. It's slightly better than GCC. We happen to use GitLab. I like GitLab personally. If you're using this in GitHub, your friend here is called Travis CI. Some of these things can't be done with the normal GitHub automations because you're going to need to set up things and actually run them manually, possibly even on your own hardware. Travis can do all these things for you. And if you're open source, you get some time on Travis that you can use for free too. So exactly what hardware and components are going to use will depend a little bit on the setup. But at least as long as you're in academia or if you have open source product, you will not have to pay for any of this. The last part here that I would strongly encourage you to use is to combine this with issue tracking. And this might sound strange. Yeah, for GROMACS, we might need it because we have hundreds or thousands of external users. But I use this in my own repositories too. If I find a bug in my own code, I create an issue. Now, this issue is reported to me. But then I make a commit, and in the commit message, I said that this fixes issue 47. This will automatically close issue 47, so I now can track that it has been closed. But if you later on type git log, I will be able to see that this particular change was a change that we did to fix bug number 47. And then I can click there and take, what was bug 47 about? So 10 years later, you're going to thank yourself for having this. And it's not really more work to do this, right? But make a habit of start doing that when you have those 10 lines of code. Don't wait until you're in my shape, because we had to spend like 5 people with a year fixing things up. Yes? So the nice thing that you can do in the issue tracker, maybe that you can, for instance, say that this is related to another issue that we also had. Or I might not be able to fix issue 47 until we have fixed issue 20. And I might not be able to fix issue 20 because that is targeted for next release or something. So that you can do fairly fancy dependency tracking. You can also say, you can automatically create to-do lists that before to do the release 2025, there are these 5 issues remaining that I need to fix. So it's, in particular, the real value here is, of course, when you have a large team that need to interact, then it's really nice to have these lists. But again, it's so easy to start with these good habits when you have 10 lines of code, so don't wait until you feel the pain that we felt. And I'm pretty much done there. We might have a minute or two for questions. The other thing I'm going to mention here just briefly is that many of you are in science and working on floating point. Floating point that Konrad Zuse invented is, I can't quite decide if it's the most beautiful or most horrible invention in computing ever. Floating point is the most obscure and complicated thing. Right? If you think that you understand IEEE 754, you don't understand it. It's worse than quantum mechanics. As a challenge, you can ask me about later on. Don't assume that line there always will return the value 0.0. And you can think about why. This leads to horrible bugs that's going to depend on the hardware you execute on. It's going to depend on the compiler you execute on. It's going to depend on the version of the compiler you use. And you're now going to be, people like me had a very nice free ride because everything was x86. You're living in a new future where you have 3 different architectures of accelerator, at least 3 different architectures of CPU. So you're going to have to get used to a much more heterogeneous world than our generation was. So be aware that floating point is very, very dangerous. To save you from that, use unit tests and automatic testing. There is some follow-up reading here, and I've mostly added that so that you have in the PDF notes. But this is actually enjoyable. It takes time, but I enjoy writing code nowadays, and I so didn't enjoy writing code 10 years ago, and that's why I would encourage you to start applying proper software engineering practices before you feel the pain. Thank you.